Hi, I'm Brian, and this is my name reaction. So today we're going to be looking at the Henry reaction, aka the nitro-aldol reaction. So to start off, we're going to get some basic info about the Henry reaction. So it was discovered by a Belgian chemist, Louis Henry, in 1895. And what the Henry reaction is basically a combination of a nitroalkane and a carbonyl compound in the presence of a base to form beta-nitro alcohols. And what the Henry reaction is really useful for in organic synthesis is creating these beta-nitro alkanols that are readily transformed into other derivatives like nitroalkenes, 2-amino alcohols, and 2-nitroketones. And so you can see the overall reaction at the bottom over here. You have a nitroalkane and then a carbonyl compound, which can either be an aldehyde or a ketone, and then you have a base. And in this case, we're going to have a hydroxide, OH minus, as a base. And online, I found that most of the Henry reactions seem to end in this nitroalkene, so I guess I'll show the reaction through to the nitroalkene. So let's move on to the mechanism. Let me just make sure the camera gets it. Sorry, it's a weird angle. So we're going to start off with our nitroalkane. So we have minus, and then we have a random R group, and this R could represent any other group. So we're going to start off with our base, and it's going to basically deprotonate the nitroalkane. So one of these hydrogens is going to basically add electrons to this carbon over here, and the hydroxide, the base, is going to pick up the H, thereby deprotonating the nitroalkane. And what we get from this little reaction over here is a resonance stabilized anionic intermediate. So we have and so we have resonance here. And so the double bond could go up to the O, and then these electrons will become a double bond here to create more resonance. Don't you just love resonance? So our resonance stabilized intermediate is then going to react with our carbonyl compound, which in this case is going to be a ketone. Actually, it doesn't have to be a ketone. It could be a ketone. So our electrons on this O are going to come back down to make a double bond, and this double bond here is going to react with this carbon, and this double bond is going to go up to the O, and we're going to create something like and what we formed is an alkoxide. And so from this point forward, the alkoxide is going to pick up a proton from the conjugate acid of the base to basically form our final beta-nitro alcohol product. And we're going to also regenerate our base catalyst that we used in the beginning, which was OH minus. So what happened next again? Yeah. We got some water. Actually, I'm gonna make that O. Scratch that. So hydrogen's gonna leave this water. We're gonna pick up this bad boy, and we're gonna end up with our beta nitro alcohol. And so most Henry reactions end in this, but online I've seen that a lot of them take it a step further and show the side reaction where it becomes a nitrile alkene. So I guess I'll show that as well. And so what happens is basically dehydration, where water leaves and then you get a double bond. So the H here is going to leave, the bond's going to become a double bond here, and that leaves, and the O will pick up the new H. And so then we will have a nitrile alkene with a water byproduct. Yep, that's basically it for the Henry reaction. So to go over, we started off with a nitrile alkane, and it was deprotonated by base to create a resonance stabilized intermediate, which then reacted with our carbonyl compound, and then the carbonyl compound, the intermediate reacted. The intermediate reacted with the carbonyl compound to create an alkoxide, and then alkoxide then picked up a proton from our conjugate acid of the base that we initially used, which was hydroxide. So the conjugate acid was water, and we have our final product in most Henry reactions, which is a beta nitrile alcohol. But then we took it a step further with dehydration to create a nitrile alkene. Yep, so that's it.